So the year is 1666, and a physicist named Isaac Newton found the law of universal gravitation, which states that every mass is attracted to each other, and the force that is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Now, the effect of gravity was primarily observed through the forces and motions of celestial bodies, such as the Earth and Sun. While these observations confirmed the validity of Newton's relationship on a cosmic scale, the direct measurement and observation of the gravitational force without the influence of the Earth or Sun remained unknown. This remained true until in 1797 an English scientist named Henry Cavendish performed an experiment to measure the gravitational attraction between two lead masses in order to find g and observe this effect on Earth. The basic premise of the experiment involved a torsion balance with two 1 kilogram lead weights attached to either end of the balance, so horizontally suspended from a fine wire. A torsion balance is an instrument that is used to measure tiny forces, such as the electrostatic force between two charges. Two suspended 160 kilogram lead weights were then attached next to the balance. What would happen is that because both suspended weights had mass, they would both feel a mutual attraction, causing the smaller balls to rotate, twisting the suspension wire. The wire would then twist until the restoring force of the suspension wire equated the gravitational force. G could then be calculated by seeing how much the angle of the torsional balance changed when we inserted the two heavy masses into the system. It's also worth mentioning that this apparatus was extremely sensitive. Elements such as your own body heat and slight wind caused by movement could jeopardize the experiment. Cavendish was able to evade this by sealing the apparatus in a box and observing it with a telescope far away. Now, let's start a derivation on how to obtain the value for g. Let's first start by drawing a diagram of the system. Ideally, the only two torques acting on the pendulum when it reaches equilibrium include the torques of gravity applied and the restoring torque of the string. Knowing this, we can formulate a Newton's second law equation at equilibrium using torque. Substituting in the definition of torque for a non-distributed force on a pendulum, we get this, where theta is the angle of deflection from its normal position without weights, and kappa is the string constant, which tells us how much the restoring force of the string is. Since I don't know my exact value for kappa, I can substitute it in using the period of a torsional pendulum. Finally, subbing in the law of universal gravitation and inertia of the system and solving for g, we get this, where the only variables we need to measure are the angle of deflection, the average period of the pendulum without weights, and the average distance of the centers of mass of the two weights. Now, let's take a look at my setup for my recreation of the Cavendish experiment. For starters, I used a 1.5 meter rod for my torsional balance with two 2 kilogram rocks as the weights on either end. For my stationary larger masses, I used two 24 kilogram kettlebells. Because my kettlebells were magnetic, I had to make sure my rocks were magnetic as well, since the magnetic force would be several orders of magnitude greater than the gravitational force. For my thread, I used a fishing wire since it has a low kappa constant, which increases the sensitivity of the system, henceforth increasing the influence of gravity. Now, my method of collecting data was to use the laser, which would then reflect onto a mirror attached to the pivot point of the torsional balance. The mirror would then reflect the laser onto the paper I had set on the ground, which had my angle markings. I could then simply use my phone to record the movement of the pendulum. This was nice because I didn't have to actively take data, which would consequently interfere with the system. I first ran a 10-hour qualitative trial of just experimenting with the orientation of the kettlebells, and my results were decent. The only problem was that I couldn't tell whether its movement was influenced by its natural oscillation or gravity. The first 2 hours were dedicated to observing the nodes in the system, and the rest were just experimenting. You could see the results yourself, though it's very clear when external variables, such as vibrations, affected the system. I found this part to be pretty interesting, as I was able to accelerate the pendulum to an angular velocity of zero both times in different directions. Even still, it's hard to say whether this was due to the weights or simply the natural oscillation of the pendulum. Next up were my quantitative trials to estimate g. I had to repeat my quantitative experiment twice because my initial estimation wasn't that great. The first time, I got an angle of deflection of 10.6 degrees, giving me a g of 1.781 times 10 to the negative 8th, a percent error of 26,585. The second time, I got an angle of deflection of 3.9 degrees, giving me 2.07 times 10 to the negative ninth, a percent error of only 3,004%. If I could change my setup, I would try to reduce the sensitivity of the system by selecting a shorter torsional balance or higher kappa constant. Although the more sensitive the better, there were way too many lurking variables in my setup that affected even the neutral oscillation of the pendulum. However, I am more than happy with my results despite the many lurking variables I had. This experiment also gave me an insight to the many struggles of experimental design. And that's all I could fit in 5 minutes. Thanks for watching.